Hi again, everyone. So today we are going to be discussing applied optimization problems. This is section 4.7. I know that the last lecture was really long, and I know it's even longer if you like stop the video and write everything down. So today is a lot easier of a day. I have one slide explaining what we're doing and then four examples, and then we're done. So trying to make it up to you a little bit. I know this is an accelerated course and this is what you signed up for, but I feel a little bit bad, so this is going to be happy Monday if you're watching this on Monday and doing it kind of in the structure that I laid out. So, all right, let's take a look. So as we know, everything in this chapter is kind of like an applied calculus. Um, I personally love optimization and related rates. I think that they're super fun, super cool, and you can do a lot of really cool things with optimization. If you have not yet already done the written assignment that I've given you, I had a problem about creating like a cute box for your cat and like material cost. And as you may know from one video when my cat was being a nightmare, I have a cat and I've definitely thought about doing this before. So like there are a lot of real world situations where this is actually super applicable. So I'm excited to be able to do these types of problems with you. So let's talk about what the strategy is for solving an optimization problem. So optimization is looking to either maximize or minimize something. So to optimize any type of a question, first we're going to want to determine the variables that we're looking at. This is very similar to when we were doing related rates. So we're going to introduce our variables. We're also going to want to draw a figure and label those variables that we determined. Drawing a diagram really, really does help us, especially in this situation. Um, After we do that, we can determine what exactly we are maximizing or minimizing. It's very, very important that we do this because the idea that we are maximizing or minimizing is going to be the equation that we're taking the derivative of. There will be times when we need to create two equations to relate variables, and we're only going to derive one of the equations. And the way that we decide that is if we're looking at the first one, for example, will be area and perimeter will be the two equations that we'll create, and we're looking to maximize area. And so that's the equation we're going to want to find the derivative of. So it's very important that we find both equations if we need two equations and understand what exactly we're maximizing and minimizing, because that's what we're deriving. Um, and then also just the range for the values if we have a special range. And we will see a situation where we do have a special range. We'll write the formula for what we're maximizing or minimizing in terms of the variable. Again, that could be area, it could be perimeter, it could be volume, it could be cost, like it could be really anything. It may involve more than one variable, so that is entirely dependent on what we're looking at. If it's area, obviously we have two variables. We probably have, if it's a box, we have length times width. We can have multiple variables. All right. Step 4 says write any equations relating the independent variables in the formula from step 3, and then use these equations to write the quantity to be maximized or minimized as a function of one variable. So if I break that down a little bit, that means if you've created two formulas because you have two different variables that you need to solve for, take the one that you're not taking the derivative of, solve it for one variable, plug it into the other one. Now you have the one that you're taking the derivative of in terms of just a single variable, and you can take the derivative of it. Do not ever take the derivative when you have two variables. That's something that we would do in related rates, so that's not something we want to do in optimization. All right, step 5 identifies domain of consideration. That is not going to be super applicable for what we're going to be doing, but you will see there will be restrictions very obviously put onto something if we have them. Um, and then it says locate the maximum or minimum value from step 4. This involves finding the critical values. So once you take the derivative, set that equal to 0 and solve, just like you normally would. This is a very common thing that we've been doing for a while now, at least a week, and it's something we're going to continue to be doing. We're going to then want to plug in that variable into the other formula to find the other solution if we have two solutions. So let's go ahead and take a look at an example. So here's an example I again provide you with diagrams. However, on like a written assignment or a homework assignment or an exam or really anything for this class, you won't be given a diagram. So you will be expected to be able to produce a diagram yourself. So this is a rectangular garden is to be constructed using a rock wall as one of the sides and wire fencing for the other three sides. Given 100 feet of wire fencing, determine the dimensions that would create a garden of maximum area. What is the maximum area? So the key here is we see that we have a rock wall as one of the sides. So the rock wall, we could draw it in. Sometimes I would indicate, like if I were to draw this, the side that we're not going to be taking into account by doing like a squiggle. And then everything that we do need to consider, I would just draw regular lines. So here's our rock wall. And then we know that we have wire fencing that goes around the rest of it. So this is our fence right here. We don't need fencing for this side, but we do need fencing for the other sides. Obviously, since it says that this is a rectangular garden, we know properties of a rectangle. We know that that means that opposite sides are congruent, which means that if we call this X, this has to be X too. That means this is probably going to be something else. Since it's a rectangle, it's probably not going to be a square rectangle, even though a rectangle can be a square if all the sides are equal. So this is going to be something else. Given 100 foot of wire fencing, determine the dimensions. Okay. Well, now that we have two different variables, we do need two formulas to relate the variables. So that's how we'll know if we need two formulas or not. Well, if we're looking for area, it's pretty natural to want to create an area formula. So let's do that. We know that area is length times width, which in this case we call X and Y. So area is X times Y. And since we're looking to maximize the area, we're going to want to take the derivative of the area function. But area is in terms of two variables here, and we don't like that. So we need to create another function that will also relate these variables. And it just so happens that we're given this other piece of information that we're given 100 feet of wire fencing. So we need to take that into consideration somehow. So that's saying 100 feet of wire fencing for this whole thing. That tells us nothing about the area. What that tells us is another concept called perimeter. We remember perimeter is just the sum of the sides. So perimeter is X plus Y plus X, which is the same thing as 2X plus Y, which they tell us we have 100 feet of. So this will be the formula for perimeter. Given that we know this, we can find area in terms of a single variable. So I'm going to solve this for Y because then it's just one less step. So Y equals 100 minus 2X. Now that I have the equation in terms of one variable, I can plug it into my area formula. So area equals X times 100 minus 2X, which I do want to distribute since I need to take the derivative of it. This is 100x minus 2x squared. Now, again, I'm looking to maximize my area. So I need to take the derivative of area. So dA dx equals, take the derivative of this right here. And we are doing it with respect to x. This is the difference between this kind of an application problem versus a related rates. Related rates, we were dealing with rates, so it was everything with respect to t. With this, we are optimizing with respect to one of the variables that we have. So this is going to be 100 minus 4x. And we know that in order to find the critical value, we have to set this equal to 0. So 100 minus 4x equals 0, which tells us that x is going to be equal to 25. We're looking to God, I can't speak, to determine the dimensions and the area. If we know x, we can very easily find y because we have y right here. So y equals 100 minus 2 times 25. Well, 2 times 25 is 50, and 100 minus 50 is 50. So y equals 50. So our area equals 25 feet by 50 feet. And that is, in fact, 1,250 feet squared. So these are the dimensions, and this is the maximum area. And if you tried plugging in any other numbers for x and y, you would find a number smaller, an area smaller than this. So this is how we would approach this type of an optimization problem. All right. Now we aren't given a drawing. So we will need to create one ourselves. So it says an open top box is to be made from a 24-inch by 36-inch piece of cardboard by removing a square from each corner of the box and folding up the flaps on each side. All right, let's start drawing. So we have an open top box, and we know that we're going to start with a piece of cardboard. We assume the cardboard will be a rectangle because that's kind of just how boxes are made. We don't know if the box is a square box. We know boxes aren't like trapezoidal, so we're going to assume it's a rectangle. And it says we cut out a square from each corner. So here's a square, a square, a square, and a square. We know that it's made from 24 inches by 36 inches of cardboard. So that means this whole length right here, the entire thing, is 24 inches, and maybe this right here is 36 inches. We've removed a corner of size we don't know yet. What size should be cut out of each corner to get the box with a maximum volume? Okay, so we don't know what the size of the corner is, so that's our variable. So we're just going to call it X maybe, X, and then everything has to be X, because we wouldn't want to take out like different sides of the corner. That wouldn't make sense. That wouldn't create a box. So we need to take out the same size from each corner. So what this tells us, if we now cut out X from here and X from here, is the length and the width of this rectangle are no longer 24 and 36, right? Because if you take out two X's from each side, well, now this is 36 minus 2X, and this is 24 minus 2X. All right. Well, what do we have? We have that we're looking for volume. So what size should be cut out of each of the corners? So since it's looking for a size, we might care about like the area, but it's looking to maximize the volume. So now we've created two ideas for equations. So first, we know that the volume of a box is going to be length times width times height, right? So the length of the box, let's say maybe is this one, which is the 36 minus 2X. The width of the box is maybe this one, which is the 24 minus 2X. And then the height of the box is going to actually be this X. When we fold up the sides, it's going to be whatever we've taken out. And so it's just going to be plain old X. All right. But now, actually, we don't really need an area formula, do we? So we could create an area formula, but we don't actually need one to plug in, because you notice that what we've done is we've created something all in terms of a single variable. So when we've created something in terms of a single variable, we don't need to plug in. The only point of having a second equation is to relate two variables, to plug in and get everything in terms of one variable. So since we've created everything in terms of a single variable here, we actually don't even need to worry about the other equation that I mentioned. So this is fine. So what we can do is we can go ahead and distribute this out. We want to take the derivative. Obviously, we're trying to optimize the volume. We need the derivative of this. We do not want to do multiple product rules. So we're going to distribute this first. So we're going to say volume equals, and I came prepared, volume equals 4x cubed minus 120x squared plus 864x. So that's what happens if you just distribute this. I haven't done anything else. All right. Well, we're still looking to maximize our volume. So then dv dx is going to be, well, the derivative of this. So this is 12x squared minus 240x plus 864. But we're looking for the critical values. We know that means setting it equal to 0 and solving. So that's 12x squared minus 240x plus 864 equals 0. But I don't want to factor something with a 12 in front. And it just so happens that 12 goes into 240 and 864. So I'm going to go ahead and divide 12 by everything, because 0 divided by 12 is also just 0. So when I do that, what I get is x squared minus 20x x plus 72 equals 0. And this is a lot more manageable when I'm like plugging in values to get an answer. Now, of course, if you wanted to just jump right into your quadratic formula, you could, but that is a lot of work, especially considering we don't use calculators in this class. I suggest trying to simplify this a little bit before you go ahead and start plugging in very large numbers. From here, I'm just going to jump to the answer. If you tried to find two numbers that multiplied to 72 and subtracted to the negative 20, you would not be successful. The answer is actually using a square root. You would need to use the quadratic formula for this. What you get is that x is 10 equals 10 plus or minus plus minus 2 square root 7. All right, so we're given two answers, but that doesn't really help us because it doesn't make sense to have two answers, right? So what we have to consider is this idea that we mentioned we would know when a domain is required. So we have to see what these values are. So 2 plus the square root of 7. Well, the square root of 7, if you think about it, is between the square root of 2 and the square root of 9, right? So between 2 and 3. If we say it's like 2.5, maybe, we're just going to guesstimate. If this is something like 2.5, you multiply that by 2, that's about 5. If you do 10 plus 5, that's 15 inches. Well, if you have a box that's 24 inches by 36 inches by 15 inches, that doesn't really seem to make sense. That doesn't fit within the domain that you would be looking for because you'd be taking 15 inches here and 15 inches here, right? Well, that's 30 inches, but that's bigger than what we have here. So you're essentially like making a box that has no sides, but is like a black hole. So that's not possible. So this is where the domain is very important. So this number is larger than what one of these sides would be. So the plus doesn't work, which tells us that x actually has to be 10 minus 2 times the square root of 7 feet. And you notice I didn't have to use a calculator to do that. I was able to just use my knowledge of where the square root of 7 lies and then my knowledge of the fact that 30 is bigger than 24 and we don't live inside of a vacuum or a black hole or I don't know science. Anyway, so this is my x value that should be cut out of each corner. So that's the side of the square. All right. What about if we're given a slightly less real world situation, but still kind of fun? We have an inscribed rectangle in an ellipse. So we're given a formula for that. That's not something you would ever be expected to know the formula of. If I said, find an ellipse, I don't expect you to know that formula. I'll give you that formula. Most of the time you will be given like real world applications of it though. So a rectangle is to be inscribed in the ellipse x squared over 4 plus y squared equals 1. What should the dimensions of the rectangle be to maximize its area, and what is the maximum area? You notice this is very similar to a circle formula, and it's just an ellipse because we've taken one of the variables and divided it by a number. A circle resembles x squared plus y squared, and sometimes you can do like x minus something or x plus something, and that just changes where the origin is. And then 1 is typically the radius, but again, now that you've adjusted it, it doesn't exactly apply to be the radius within an ellipse. So let's go ahead and take a look at how to maximize this kind of a thing. Well, since we're looking to maximize its area, obviously we need an area formula. So let's go ahead and first off create an area formula. Well, for the rectangle, since we're looking for the dimensions of the rectangle that would maximize its area, I know that area is length times width. Well, let's consider this diagram right here. If we have this to be the length and this to be the width, we need to create a rectangle of some x value and some y value that would maximize it. So if this is the maximum and we don't know what this value is here, this is x, then the length of this rectangle has to be 2x, right? Because if the distance from here to here is x, just based on the fact that this is on an xy plane, then the distance from here to here is also x. Now, you might be thinking it's negative x, but if we're thinking in terms of distance, we don't think negative. And so the actual distance from here to here is a total of 2x. So the length is 2x. And the width, we're going to use the same exact reasoning. So the distance from here to here, I'll choose a different color so that it's a little bit more obvious what I'm talking about. The distance from here to here is y. Whatever y is, it's y. But also the distance from here down to here, since this is going to be positive x, negative y, is also going to be y if we're thinking about just distance being positive. And so the distance in total here is 2y. And so your area is 2x times 2y, which is the same thing as 4xy. So this is good and all, but again, you notice we have an x and a y. So obviously we need another formula to relate these two, which is why we're given this right here. So we'll go ahead and solve for one of the variables to plug in. I might suggest solving for the y just because we only have to consider the square root versus the x squared. We'd have to multiply by 4 and then square root. So if we take x squared over 4 plus y squared equals 1, we can also say y squared equals 1 minus x squared over 4, which if we square root, I'm only going to write out the positive side, obviously plus or minus. So we have the up here and the down here version. I'm just going to write out the positive version to start, and then we'll take into account the negative version when we're looking at area and stuff. So it's the square root of 1 minus x squared over 4. So now we can plug into area. So area is 4x times the square root of 1 minus x squared over 4, which is our y. I don't love having fractions in here, so what I'm going to do is I'm going to adjust this inside here. And the way that I'm going to do that is by multiplying this by 4 over 4 and this by 4 over 4. And when I do that, or by multiplying just kind of everything through by 4. And when I do that, what I actually wind up with is going to be 2x times the square root of 4 minus x squared. If you'd like a more detailed explanation, I can give you that real quick. If you'd rather, you could think about this as, write this as 4 over 4, and then put all of this. So I'll write this and then I'll erase it. 4 minus x squared over 4 if you create common denominators. And then what you can do is write this as a square root up here, square root down there. If you pull this 4 out, square root of 4 is 2. 4 divided by 2 is 2, which is where this 2 comes from. And then you're left with the square root of 4 minus x squared. All right, so all I did was rewrite it a little bit. Now, you could leave it like this, and you could also solve, but I would rather rewrite it like that because it just makes it a little bit easier for us to solve. So I am going to erase this. If you want some further explanation on this, I'd be happy to give it to you. All right, so I've rewritten that, and now we want to go ahead and take our derivative. So this just kind of helps with our derivative. So the derivative a prime is equal to, well, this is a quantity times another quantity, so we have to use a chain rule. Not chain rule. We'll have to use a product rule and then a chain rule. So we do need chain rule afterwards. So this gives us first times the derivative of the second, so 2x times the derivative of this. We have to remember square root is the same as a 1/2 exponent. So this is 1/2. Keep what's inside. Subtract 1 from the exponent, so 1 minus 1/2 is negative 1/2. And then we have to multiply by the derivative of what's in here. So the derivative of 4 is 0, but the derivative of minus x squared is minus 2x. All right, so that's first times the derivative of the second. Now we do plus second, which is just the square root of 4 minus x squared times the derivative of the first, but the derivative of 2x is just 2. All right. Now, if we were to simplify this thing, this goes into our denominator as a square root. Again, I'm not going to get into the algebra of all of this because this is just algebra and simplification. And so if you want to verify that this works, I encourage you to write out the algebra. Otherwise, if you just take my word for it, I promise that this works out. What this is actually equal to is, again, I have it right here. It's 8 minus 4x squared over the square root of 4 minus x squared. And this is what the derivative is once you simplify this whole thing. Now that we have the derivative, what we can do is we can set it equal to 0 and solve. So what we know is that 8 minus 4x squared over 4, the square root of 4 minus x squared, I'll raise that to the 1/2 power, equals 0. All right, and we can go ahead and solve this value. So if we multiply both sides by our denominator, what that actually gives us is that 8 minus 4x squared equals 0. If you added this over, divided by 4 and square rooted it, what you actually get is that x equals plus or minus the square root of 2. And we do have to remember the plus or minus here. But if you consider what we started with, again, we only want one x value. This is very similar to the one that we just did. We said we had two values, but one of them didn't make sense. If we want an x value, we have the plus or the minus. We have to ask ourselves, would it make sense to have a negative x value? And if we're thinking about x in terms of distance, it would not make sense to have a negative x value. Because if we're saying that the length of this thing is going to be a negative square root of 2, that makes literally no sense, because that's saying that we have negative distance. And again, we're like inside of a black hole or something. Doesn't work. So we actually want just x is the square root of 2 positive, because that's the only way this will work. So if x is the positive square root of 2, we can find what y is going to be pretty easily just by plugging into our y equation right here. So y is right here, actually. That's y squared. This is regular y. That's 1 minus square root of 2 squared over 4. So y equals just 1 over the square root of 2 when you go ahead and simplify this thing. And again, so that's the square root and the square will cancel out. That's 1 over 4, 1 minus 1 over 4. Oh, that's 2 over 4. I don't know why I thought that was a 1. This is a 2 here. I can't read my own writing. 1 minus 2 over 4 is 1/2, but the square root of 1/2 is 1 over the square root of 2, just because the square root of 1 is 1. All right. So now we can go ahead and find the area itself. So what are the dimensions to maximize the area? It's going to be x is the square root of 2 and y is 1 over the square root of 2. And then the area we just can plug into this formula here. So area is going to be 4 times x, which is the square root of 2, times y, which is 1 over the square root of 2. But the square root of 2 and 1 over the square root of 2 cancel out. So our area is just 4. All right, I know this question was probably a little bit harder than the other ones. Maybe it makes a little bit less sense. So if you're struggling with this one, but if the other ones make sense for you, I wouldn't worry too much. If the other ones are still a little bit iffy, I'd practice with those. I practice with the more application type questions. All right, I've got one more question for us to go through. Another box question. We love our boxes in calculus. A rectangular box with a square base and an open top has a volume of 216 cubic inches is to be constructed. What should the dimensions of the box be to minimize the surface area? And then what is the minimum surface area? Okay. So we have to ask ourselves, what are we given? Well, we're given volume and we're asked for surface area. So we clearly have to create two formulas here. We do have a drawing up here, but if we weren't given a drawing, we were told that it's a rectangular box, but it has a square base. Well, since it's a square base, we know that all of the sides of the base are equal. Since it's a rectangular box, we know the height is different. So the square implies that these two bases, maybe you're just x and x, or whatever you want to call it. You can say b and b if you'd rather for base. And then the height is going to be a different value. Well, volume, we know, is going to be length times width times height, which in this case is x times y, which is x squared y. So that one's pretty simple. But we're not looking to do anything with volume. And in fact, we're given what the volume is equal to. So the volume is 216. So we're not looking to maximize and minimize the volume. We're looking to minimize the surface area. So remember, surface area is the three-dimensional version of area. So surface area just means that you're going to take the area of all of the surfaces that you have and add it up. It is important that this specifies that we have an open top, because that means we're not considering the area of the top. We want the area of the bottom and then the area of the four sides. So that means that surface area, I'll call it S, is going to be the sum of all of the areas that we have. So then we'll just have to use our area formulas. So the area of the bottom is going to be the area of the square, which is just the side squared, or x times x. That's x squared. Plus we have 4 of these faces right here that all have a base of x and a height of y. So we have 4, and then the area here is x, y. So this will be our surface area formula. This is what we're trying to minimize. Well, naturally, since we have an x and a y, we need to solve for just a single variable using the other equation. So you can choose whichever variable you'd like to solve for. Typically, we do y just because like that's what we write things in terms of. But if you want to do x, you can. It would be a little more complicated here because it's a square, so I suggest doing y. So y is 216 over x squared. Knowing this, we can plug it in here. So s is x squared plus 4x times 216 over x squared, which if, I'm going to cover the little diagram now, if we rewrite this, this is the same as x squared plus this x will cancel out one of these. And then if you multiply the 4 into the 216 up here, we get 864 over x. All right, now, again, we're looking to minimize the surface area, so we need to take the derivative of the surface area. Derivative of x squared is easy, that's 2x, and the derivative of this guy, you should rewrite this as plus 864x to the minus 1. Again, remember, if this is a 1 exponent, you want to write this in the numerator, you negate the exponent. We want to do that because now we can use the regular power rule. So take this, bring it out front, so that's minus 1 times 864 is 864x, and then subtract 1 from the exponent. So -1 minus 1 is -2. And you may rewrite this as 2x minus 864 over x squared as well. Since we've taken the derivative, we can now set it to 0 and solve. So 2x minus 864 over x squared equals 0. But we don't like it when we have things in our denominator, so we're going to go ahead and multiply everything with x squared to get rid of that. So this will get rid of the term here, multiply x squared here, we get 2x cubed minus 864 equals, but then x squared times 0 is just 0. And then we can go ahead and solve this, right? Move this over, divide by 2, and cube root it. And what we get is that x is just simply the cube root of 432, which is half of 864. Typically, you'd want to leave your answer like this because, again, you're not using a calculator. So I'm not going to give you a decimal version of that because we don't use calculators. So if x is this and we're looking to find the dimensions of the box that would minimize this, then y is just plugging into this right here. So then y equals 216 over the cube root of 432 quantity squared. So this is your y, this is your x, and the dimensions of the surface area, let's see, the minimum surface area is just plugging into a surface area formula. So the surface area is x squared, which is this, so that's the cube root of 432 squared plus 4x, which again is the cube root of 432 times y, which is this right here. That's 216 over the cube root of 432 squared. And that's a really ugly answer, but that just is your answer. All right. I hope this one was a little bit shorter. Like I said, really make sure that you're understanding the application questions. If the last one threw you for a loop, that's okay. I mean, you could definitely look at that again, but the 3 application questions were a little bit more important. All right. So if you have any questions, just always let me know. If not, then I will see you for the next lecture.